to the war and the need to find alternative sources of energy to power electric vehicles. We were funded both by government to do basic research on high-temperature lithium batteries, and later industry came in to support us to do some applied research, which led to the development of a sodium nickel chloride high-temperature battery as an alternative to sodium sulfur. And that program was highly successful. It resulted in a development of buses and cars in conjunction with help from Anglo-American in South Africa, Beta R&D in the UK, and Daimler-Benz in Germany. But there was one major spin-off from this high-temperature lithium batteries. We also were following what Argonne was doing in the United States in the development of their lithium aluminium iron sulfide battery, and we replaced the iron sulfide cathode with iron oxides because they were less corrosive. We looked at two iron oxides, Fe3O4 and alpha Fe2O3, and discovered that these materials operated by a beautiful lithium insertion ion extrusion reaction. Unfortunately, the operating voltage of these systems was too low for practical use. But the beauty of these reversible insertion and extrusion reactions was that the cubic close-packed oxygen array remained intact during the electrochemical process. But in each case, the Spinel structure was regenerated on charge, particularly in the case of Fe3O4. If one started with alpha Fe2O3, which was hexagonally close-packed on charge, that didn't go back to that particular crystalline form, but rather to gamma Fe2O3 Spinel. So there was something going on in the stability of Spinel framework structures and rock salt. The low voltage of the systems didn't interest Anglo-American, our sponsors in South Africa at all. So I wrote to John in 1981 to ask if I could come and spend some time with him and to investigate the reactions of Spinels, and in particular Fe3O4 and Mn3O4 at room temperature. When I arrived at Oxford in 1981, John called me aside and he said, well, you know, Spinels are really like gems. They are line phases. Where's the space for the lithium? And Spinels are indeed like gems. The most famous Spinel, I think, is found on the Black Prince's on the Imperial State Crown. It's called the Black Prince's Ruby. You can see it there in red, but it actually turned out to be a Spinel rather than a ruby. But we went ahead and looked at the reactions of lithium with these two Spinel compounds and found that the B2O4 framework of the Spinel structure remained totally intact as the Spinel, as lithium was inserted into the Spinel. But in order to create the space, the cations on the tetrahedral sites had to be displaced into octahedral sites. I remember Bill David and I, who had just done the work on the Fe3O4 and noticed these structural features, we took the results to John, and it wasn't 5 seconds or 10 seconds before John said, well, if that's the case, what we have to do is to replace the tetrahedral site cation with lithium. And that was the start of the lithium manganese oxide project. Peter Bruce joined the team as the electrochemist. So this is a shot of the staff of the ICL in 1982, and you can see John there in the center. But there were some other notables at the ICL at that time. One was Peter Dickens, who turned out, or was the PhD supervisor of Stan Whittingham. They'd been working on bronze structures and hydrogen insertion in the late 1960s. But out of this, since John Goodenough's time, there have been several what I call ICL lithium battery notables, John in particular, of course Stan Whittingham, 2 Nobel laureates, Bill David and Peter Bruce, who worked on the manganese Spinel, and as Manthiram said earlier, he initiated some of the very early work on polyanionic structures such as iron sulfate. I can't not show this photograph. It was taken on the 9th of October last year when the Royal Society presented John with the Copley Award, and it just so happened that the Oxford Spinel team from 38 years ago was present for the dinner. Peter Bruce on the left and Bill David on the right, and me in the middle, and of course John in the front. But of course, as many of you might remember, 9th of October was the day that the Nobel Prize was announced, and so it was a double whammy for us, and we had an excellent dinner that evening, and just lovely that the Oxford Spinel team of 4 was there to celebrate with John. In 1983, I went back to South Africa, and there the CSIR team were the first to extract lithium electrochemically from the Spinel at 4 volts. But it was a little bit later on, in the late 1980s, that we realized that Sony and Sanyo and National Panasonic in Japan were beginning to talk about using Li-204 as a 4 volt in rechargeable lithium batteries. So we jumped back on the bandwagon and looked at the lithium manganese oxide phase diagram in detail, and noticed some very important factors, that if you increase the manganese 4 manganese 3 ratio, you could do this, but you could do this by increasing the lithium content in the Spinel electrode. Although this slightly reduced the capacity of the electrode, it suppressed the Ontella distortion and enhanced cycling stability at 3 volts. It suppressed dissolution at high potentials and eventually found its way into lithium-rich commercial Spinel products. A couple of years later, in 1993, John's layered lithium cobalt oxide had already taken the world by storm in being used in the first lithium-ion battery products. Layered lithium nickel oxides were also known, but there wasn't an anhydrous lithium manganese oxide. So we started trying to think of ways to produce a layered lithium manganese oxide, and we started off by looking at Li2MnO3, which is rock salt. It's electrochemically inactive, but used it as a precursor to try and make a layered lithium manganese oxide structure. It so happened that Jim Hunter in 1981, when we were working on Spinels at Oxford, was also looking at Li-204, but in his case, he was leaching lithium and manganese oxide to make lambda MnO2 as a electrode for a primary lithium, high voltage lithium cell. But we noticed that this acid treatment leached out lithium during the chemical reaction. And if you look at the formula of Li2MnO3, it's Li2O.MnO2. So we took Li2MnO3 and used sulfuric acid in a similar sort of fashion, to strip out some lithium from the manganese oxide structure. Although this was accompanied by some lithium proton exchange to yield a charged product that you see on the top left. Once one reinserted the lithium under non-aqueous conditions, either chemically or electrochemically, we created a discharged cathode, which consisted of 2 components, Li2MnO3 and a layered Li-MnO2 structure. So this gave us some thoughts of using Li2MnO3 to stabilize layered materials. In 1994, I left the CSIR in South Africa and headed towards Argonne National Laboratory in the United States. And we used the work that had been done at the CSIR largely as a platform to continue studies on lithium manganese oxides. And we used this idea of Li2MnO3 to stabilize layered NMC type materials. The strategy there was to, again, embed Li2MnO3 as the inactive component and to stabilize the structurally compatible active layered NMC component. And this idea is analogous to the structure and electrochemical operation of gamma MnO2, which consists of two components, an inactive beta MnO2 component, which is structurally integrated with an electrochemically active ramslide MnO2 component. These what I call layered materials, Li-2MnO3.LiMO2, worked in a certain sense quite well. It was Jeff Dahn who first pointed out that if you took these materials and charged them above 4.5 or 4.6 volts, you could strip lithium and oxygen out of the structure and increase the capacity of the material considerably by as much, and to get capacities of about 250 milliamp hours per gram. Unfortunately, these materials suffer from voltage fade, which is attributed to structural instability and particularly the migration of transition metals into the lithium layers. But if you control the reactions and narrow the voltage window, you can actually get very good cycling performance from some of these materials. They only operate really well at low current rates, and there is some hysteresis on charge and discharge, which doesn't count in its favor as regarding power output. So there were these problems associated with these layered materials, and we're still working on them at Argonne. And we've looked at the problems, and we extended the concept of using these structurally integrated materials and extended that to a three-component system where we introduced some Spinel into these structures. And the motivation behind that was to use the Spinel as pillars to stabilize layered structures. And we all know that in the Spinel structure, 25% of the transition metals are located in the lithium layers. And the compatibility of Spinel and Li4-MN5O12 and Li2-MnO3 can clearly be seen on the TEM image on the right-hand side, where you can see this beautiful integration between the two components. The reason for that is that the lattice parameters and the X-ray diffraction patterns of these two materials are almost identical, yielding this beautiful nanocomposite structure. So we've advanced our knowledge of these materials, and by 2015, we had scaled up some of these materials and had discovered that if one introduced between 5 and 10% Spinel, which you can see in the green and the blue plots, on the left-hand side, both cycling stability and on the right, rate performance of these materials is considerably improved if you have between 5 and 10% of Spinel within the structure. TM images, however, have demonstrated that it's more likely that the Spinel in these cases is found at the surface rather than within the bulk. So I just want to end off with some comments as to where we are now with work on Spinel-related materials. And instead of using manganese spinels as a stabilizing agent, we're looking at lithiated spinels now, because and there's this whole family of lithiated cobalt spinels that are fairly unique because they can be synthesized in air at 400 to 500 degrees C, unlike many of the other lithiated spinels, such as the manganese systems, and of course the lithiated nickel spinel has not yet been made at all, chemically or electrochemically. But a lithiated spinel has a rock-solid structure, as does these composite Li2-MnO3.LiMO2 structures. So it seems as though it might be more worthwhile and more compatible to use a lithiated spinel rather than a stoichiometric spinel, which has got lithium in the tetrahedral sites. Another advantage is that relative to manganese and nickel, cobalt has a low propensity to migrate during the redox reactions in these composite electrodes. What we have found fairly recently is that aluminium substitution in these lithiated cobalt spinels does some really wonderful things. It changes. If you look at the left-hand side, the black dots represent the lithiated Spinel curve, and you can see between, if you start off on the right-hand side and extract lithium, it operates in a two-phase reaction process up until about 70% of the lithium that's been extracted. Then unfortunately, we've got some layered LiCO2 material in that sample, which is a little bit difficult to remove. If you look at the aluminium substituted material in red, the aluminium substitution changes the nature of this reaction radically from two-phase behavior to what seems like an apparent single-phase process. Aluminium substitution also increases the cell voltage. And even more exciting is that the lithium cobalt aluminium oxide, a lithiated spinel, like lithium titanate, LTO, a titanate spinel, both of those are zero-strain electrode materials. There's virtually no change in the lattice parameter of both these compounds. So now we have a really nice model system where we can combine an LCAO cathode with an LTO anode. And what are the implications now of designing a 2-volt all solid state lithium titanate, lithium cobalt aluminate cell? I think just from the question of time, I'm not going to spend too much time on this slide, except to say that some very elegant structural work has been done at the Advanced Proton Source by E.J. Lee. And the realization now is that the aluminium substituted material contains what seems to be about 2% aluminium on the 16C sites, which then impacts the diffusion of lithium through the 8A16C, 8A16C tetrahedral octahedral site network for lithium diffusion. And this gives rise to the slight change in the electrochemical profile. So in conclusion, the Spinel story is not yet quite over. It's been a long time since we started working on it, but there's still some exciting things going on. And although nickel-rich and NCA and NMC are still in vogue, Spinel-stabilized lithium and manganese-rich materials still hold some promise for the future. And if I can go back to the original patent that John and I took out in the early 1980s, it seems as though we might be closer now to capitalizing on this 37-year-old concept of an all-solid-state Spinel cell, because the title of our patent was solid-state cell wherein an anode, solid electrolyte, and cathode each comprise a cubic close-packed framework structure of the Spinel. So we'll see. We just need to get a really good Spinel solid electrolyte now, and we could have a really interesting all-solid-state system. So just finally, just some comments about life and the significance of being 98. I've known John for almost one half of his lifetime. And the second half of John's life has been just as prolific, if not more prolific, as the first, capped by his enormous contributions to lithium-ion battery science and technology, and of course with the award of the 2019 Nobel Prize in Chemistry last year at the age of 97. Very few will emulate his lifetime efforts and achievements. And just finally, I'd just like to quote from William Makepeace Thackeray, who's a relative, he was an English novelist in Victorian times. And it just seems to me that William Makepeace Thackeray's and John Goodenough's philosophy on life have been the same, particularly when you take into account the fact that John was 97 when he won the Nobel Prize. And this is probably a message for the younger generation. Do not be in a hurry to succeed. For what would you have to live for afterwards? Better make the horizon your goal. It will always be ahead of you. Thanks very much.
I thank Professor Thackeray for sharing us with the great history to discover, the spinel oxide. We collect many questions from the broadcast, but because of the time is not enough, so we will transfer the question to you by email. Here, maybe we just answer one question. Because everyone know you discovered, the spinel cathode material with Professor Goodenough. So the audience, they want to know, is there any general model to discover the cathode material? And what about the future direction for the oxide cathode material?
Yeah, well,
thank you.
Yeah, well, an interesting question. You've got to dream and you've got to think big, and sometimes you've got to have quiet times just to reflect. The world has become so busy that one needs time, I think, to be innovative. Lithium metal oxides are reaching, I wouldn't call it saturation, but so much is known now about them relative to what was known 40 years ago. But I think that some of the developments these days, there's so much work going on around the world on all the major continents. So it's difficult to find something that's new, but every now and again, and I take this, maybe it's a small example, but one of the aluminium substitution in the cobalt, I think that we've hit on something which is really intriguing, which is giving us new life to maybe do things that might help us just improve the performance of lithium-ion batteries in the long term.
Okay. Thank you. So John, yes, thank you. So John, now next speaker, John, please.